ทำไมมันไอ้คนที่จะเลือกคนละอันใช่ป่ะไม่เกี่ยวกันมันจะมีความจำแบบกับคุณก๊อฟไปตรงไหนว่าเป็นเยอะอยู่เทียบนะครับเป็นหลายๆเป็นเทียบกับข่าวนี้อันดีกว่านี้ไม่ก็คืออันเป็นการเหมือนหมดเลย
Good evening.
Maybe you want to stay time at work. You want to no. This is the from the new one. Because before starting, you still need to check, right? What's in the list of like NPL they say the AP of the DL, yeah, so I think the nationality and I check it.นี่ลูกน้องผมใช่ไหมหน้าเขาเลยผมจะเป็นลูกน้องเลยลูกนี่มันยังไงมองแต่แม่ที่เขาเลยล็อกที่ไม่ถึงจับเยอะเลยthey won't let you on that. Wow, stay on the night here. And I thought Bangkok. I thought you were going to go out somewhere. Like Geomechanics, domain. Meetings are once a month. We have scoring. So you study, yeah, yeah. I was gonna say, got must be or not many university and I can't that section and give you try to bring and Cost of the section in the world. Yes.
ตีโกรธเลยเนี่ยทำโกรธ
Good evening, everyone, dear member and distinguished guests. My name is Pathanan Thamrujikun. I'm the member of SPE Young Professional Board. So I'm here to help supporting running this meeting for tonight. I will be the MC for tonight. On behalf of SPE Thailand Board of Directors, I would like to welcome you all to SPE Technical Monthly Meeting. Thank you for being here tonight, and we are happy to see many oil and gas organizations here, government representative, and also academia from upstream oil and gas. Also, special welcome to student chapter. Please raise your hand for the student. Yeah. Thank you for joining us today. But before we start our presentation, please take note of the safety announcement. There are no emergency drill planned today, so if there any alarm, so be calm. Look for the nearest emergency exit, which are all clearly marked. The hotel staff will assign to this ballroom will guide you to the exit area and assembly point outside of the building. It's important for everybody to stay safely. You remain calm and don't be rushed. Also, if you observe any suspicious activity, please do not hesitate to inform our staff. So here is our agenda. Our activity. So you go for presentation, then closing remark, and end with lucky draw. Section announcement. You know that SPE vision is to collect, disseminate, and exchange technical knowledge. And our SPE vision is to enable our industry to share this knowledge and meet our future energy needs. So our purpose is sharing both information and hospitality. That's why it's bring us here today, gather together. And these are the companies support us for this, our Thailand meeting, technical meeting for this season. For any of you just join us today for the first time, if you want your company to be in this presentation or in another promote event, please feel free to reach out to us. We appreciate your support, and of course, our society needs you. Here is the SPE member valid membership. Today we have more than 700 membership, approximately 400 from professional member and 300 for students. We have both Chulalongkorn University, Suranari, Prince Songkhla, Chiang Mai University student chapters. However, we observe that 100 of our professional members from last year haven't renewed the membership yet, so please consider renew it. Also, and all of us, please invite your colleague to join our event and being SPE member. SPE Thailand is still the largest professional oil and gas industry organization where you can meet and greet in a relaxed environment. There are plenty of reasons why you should join SPE. We are the most active SPE section in Southeast Asia. We offer a regular opportunity to network, share knowledge, and socialize with peers within our industry. So let's move on our main course for today. Ladies and gentlemen, we will now continue with main presentation. Can we please to have Kun Gasian on stage to introduce our keynote speaker?
Thank you very much. For those who do not know me, I'm sure you know me. My name is Kasi and I'm the program chair for SPE Thailand. It is always my honor to do the introduction for the speakers. But before I do more, it is very, very appreciated that, we don't have a chance before to have a Saudi speaker in Thailand. This is kind of like a new opening. So please enjoy Thailand before you leave. You're leaving tomorrow morning, right? Or tonight? So yeah, please enjoy together with us. Okay, without further ado, let me do the speaker introduction. So our speaker this evening has worked in different upstream positions since 2011. These include drilling engineer, lab scientist, and reservoir engineer. Currently, he is leading the drilling geomechanics research area in Saudi Aramco Advanced Research Centers, so-called XPEC. Okay. He is developing tools for modeling the impact of dynamic events on wellbore rock failures. He has published many tools. He has published multiple peer-reviewed articles. Sorry, I couldn't see anymore. Authored several granted patents and received multiple awards, including the 2020 SPE Gulf Coast Region first place winner of the PhD Students Paper Contest, and the finalist in the 2018 Abu Dhabi International Petroleum Conference Young Engineer of the Year Award. Ladies and gentlemen, please join me for a warm welcome our speaker this evening, Mr. Hussain Al Bahrani, distinguished lecturer from Saudi Aramco. If not, then I can change the slide for you. Okay.
Thank you, Cassian. Thank you so much. Hello, everyone. It's a pleasure for me to be here. Thank you for having me in Thailand. This is actually my first time ever in Thailand, and unfortunately, even though I'm leaving very soon, but it's my pleasure to be here, and it's an honor to present to you this topic today. Before I begin, I have to mention that the primary funding for those lectures is provided by the SPE Foundation through members' donations and the contribution from offshore Europe. So my name is Hussain Al Bahrani. I work for Saudi Aramco Research Center, working mostly in drilling research. Today I'll be presenting to you a topic about improving the way we do drilling geomechanics. So the drilling industry has long relied on pre-simplifying assumptions and pre-drilling models to predict rock failure and recommend safe mud weights for drilling engineers to prevent MPT, non-predictive time. So the goal of this topic is to show how we can overcome those oversimplifying assumptions and also enforce the application of drilling geomechanics principles in a more dynamic and responsive manner that fits the nature of drilling operations. So I'll be taking you through the full journey, starting from the background information about how we do drilling geomechanics currently, and then I'm going to move to the model development and its validation through experimental work. Next, I will go through some field applications of this modeling work, and I'm going to end the talk with some future outlook for this new methodology. So to begin, there are some basic terms and concepts I'll be using throughout the talk today, and I would like to cover them here. The first concept is the drilling window. The drilling window is basically the allowed safe range of bottom hole pressure exerted by the drilling fluid density or the mud weight and the frictional pressure from the mud flowing upward in the annulus. Now, as you can see here, there are two limits to the window. So you have an upper limit and a lower limit. If you violate the upper limit, which is the frag gradient, you initiate a tensile failure, such as the one you see here. If you initiate that tensile failure, you are basically creating a fracture. The fracture is a way to lose circulation. So the way we see this kind of failure on the surface, on the rig floor, is by losing drilling fluid or mud circulation. Now, on the other end, if we violate the lower limit, which is the wellbore stability limit, we will initiate or incite shear failure, which is wellbore enlargement. Now, with wellbore enlargement, you can get cavings, enlarged rock fragments, hole cleaning issues. You can get a stack pipe incident, and you can get a collapsed wellbore in some severe cases. So in all of those problems that we can get or experience from those two failures, the fracture and the enlargement, those are the major causes of non-productive time in drilling operations. So by avoiding those causes, you can make the drilling operation more efficient and more profitable, basically. Now the question is, how can we detect those failures? The ideal way to detect those failures is from image logs. As you can see here, we have two examples of image logs. That's an ultrasonic image log, and the dark spots you see here, they correspond to an enlargement. So from this image log, we know that the well is experiencing the failure you see here in this image. In the other image log, which is a resistivity image log, you can see some black streaks. And those black streaks is basically the induced fractures. That's the tensile failure that is causing the draining fluid to not return all the way back to the surface. That is causing the lost circulation. Now, that's only the ideal way to detect those failures. In the most routine type of operation, we don't have those image logs. So we are only left with this equipment here. That is the shale shaker. Now, that's the equipment that receives the mud coming back from the annulus. So if we observe the shale shaker and we can see some abnormalities like enlarged rock fragments or cavings on the surface of this equipment, we can conclude that the wellbore is experiencing wellbore enlargement. On the other end, if the amount or volume of the returning fluid on the shale shaker is not equal to the amount you are pumping in, then it means you have some kind of tensile fracture. It could be induced or a natural fracture, of course. Now, the next question, what does a drilling engineer get to plan for those two kinds of failures, the tensile failure and the shear failure? Well, the drilling engineer will get what you see here, this curve right here. That's a pre-drilling geomechanics model. You get a curve that recommends the minimum mud weight and the maximum mud weight. And you can select your mud weight based on this curve. Now, these kind of recommendations that drilling engineers get, they do suffer from some shortcomings. The most glaring one out of those is that this model is a pre-drilling static model. It means that this model is built based on offset wells data. So before we drill our future target well, we collect information from nearby offset wells, and we try to come up with a recommendation and build this model based on the offset wells data. As we are doing that well, the information might turn out to be not as accurate as we hoped, but we still stick to those recommendations, and that's why those models are usually static models. So whatever two limits you have for the mud weight, those are the limits that the drilling engineers will stick with when selecting their mud weight. The next issue is those models estimate rock failure based on, I think it's not working. It's not working anymore. Can go back one more? Okay, excellent. So we have a stress strain curve. That's basically how we test a failure in a rock sample. So we apply stress and we see how it fails. So that's the strain, the deformation. The natural response of failure for a rock sample is it starts with a linear fashion and then it goes to a plastic nonlinear fashion. Most solutions used in the industry, they rely on the assumption that the failure takes place only in the linear fashion, which then leads to some inaccurate recommendations to prevent those failures. Can you go next? The assumption here is the wellbore shape. Most models, actually I can say with good certainty that all models used in the industry right now, they always assume that the wellbore shape is perfectly uniform, so it's perfectly circular or perfectly elliptical in shape. However, if you run any kind of multi-arm caliber log or a 3D caliber log, you end up with this 3D image of the wellbore. So this shows you the actual shape of the wellbore. And as you can see here, the shape of the wellbore is anything but uniform. It can be as far away from a uniform as you can see here. So you have irregularities, you have different shapes at different depth points. So that's the issue that we need to improve on to get a better modeling scheme. I'm going to move on to the next part of this talk, which is the model development. I promise you this is going to be the only math you will see in all of this talk. But basically, to overcome the issue of linear elasticity, we are proposing the use of finite element modeling. Here in this curve, you see again stress and strain. So that's the force we apply on a rock sample, and that's the deformation, the strain that is experienced by the rock sample. And that is the actual curve we produced in the lab for a sandstone reservoir sample. And as you can see, the initial behavior is nonlinear. Then it goes into the linear elastic behavior all the way to the yield point. As you know, elastic behavior means it's a reversible damage, reversible deformation. At the yield point, you start to go into the nonlinear behavior and the plastic permanent damage. So the main goal of using finite element modeling is just to reflect the nonlinear behavior here and the nonlinear permanent behavior here for the deformation of the rocks. So what we end up with is two components of deformation: elastic, which is the non-permanent, and the blastic, which is the permanent one. Now, the blastic deformation is calculated using the blastic floor theory, which is just the rate of change of this buoyant with respect to the stress. What we end up with at the end is a scalar value for a blastic strain. So that's our main point of improvement, calculating the nonlinear deformation of the rock and under different stresses. So that's the goal. Now I have to emphasize that the use of finite element modeling is not really something novel in the industry. You can go and find papers as old as in the 60s or 70s that use finite element modeling and plasticity for doing geomechanics. However, it's still not as widely used in available solutions, especially commercial solutions for commercial modeling, for geomechanics modeling. But I have to emphasize this point here. Now, I would like to talk about the integration process between finite element modeling and machine learning algorithms. We are doing this integration using something called image analysis. In this case, you can see a CT scan of a borehole in the lab before we fill that borehole, and then a CT scan of the same sample after it has failed, after it had failed. The goal of this analysis is to try to get numbers out of images, basically. So we want to do a quantitative analysis on images. So the role of this analysis is to read the pixels in each image and then get radial measurements from that image. And as you can see here, if we can go and read the pixels in that CT scan of the failed sample, we can create a failure map of the borehole with actual radial measurements in every location in that circumference. So that's the main goal of this image analysis. It can tell me where the well borehole has failed and by how much it has failed. Here's the same analysis, but with a different lab experiment. In this lab experiment, as you can see, the borehole has failed in a peculiar fashion. It has failed in this direction only, probably due to some heterogeneities or localized weakness. However, again, when we run the same code or the same images in the image analysis scheme, we end up with the same failure map. Can you click one more? So you can see here that the CT scan failed borehole agrees quite a bit with the radial measurement we generated from that image. So that's basically the main goal. We want to convert an image into radial measurements to quantify our failures with more accuracy. And we can do the same thing not only for lab images, as you can see here, but we can also do it for field-based images like image logs. Can be ultrasonic image logs or resistivity-based image logs. Now, I would like to go over the integration process between the finite element model and the machine learning algorithm. And the reason I want to do that is to emphasize the role of the image analysis. So we have this lab sample you see here. So that's a piece of rock that we test in the lab. And as you can see, there is a borehole drilled right into the center of it. Now, after we fill that borehole, we can take a CT scan across different depth points, different cross sections along the axis of the borehole. And as you can see, the shape of the borehole after it had failed is different from one depth point to the next one. Now, the role of the image analysis is that it will take each CT scan and read the change in the structure of the borehole at every depth point. One more click. Okay. So if you look closely here, that's the borehole before failure in the specimen from the lab, and that's the borehole after failure based on the CT scans. And if you look at the sample from the top, after the test, you can see that the structure of the borehole is changing from one depth point to the next one. So what we end up with in this case is instead of one data point from one lab experiment, we can end up with thousands of data points based on the failure in each coordinate in that 3D space for that sample. So that's the main advantage of this image analysis technique. Again, that's the look of the sample from the bottom of the core sample. And again, as you can see, there are clear variations in the shape of the borehole if you look from the bottom or the top, which is reflected in the CT scans as well. Now, that's the last step of the integration between finite element and machine learning algorithms. So what we are doing here is that we are telling this machine learning algorithm is that this borehole, when subjected to those forces, it will fail to generate this borehole you see here, which is what we know from the image analysis. So I can improve the training of that algorithm by adding data from different wells and different experiments to then produce a model that can predict rock failure at a more accurate level than the conventional methods. Here I'm going to move on to the next part, which is the validation through experimental work. Now, the idea here is to showcase how we can apply this modeling scheme in lab environment to provide some sort of validation. In this case, we have this rock sample you see here. It is 20 centimeters by 20 centimeters. The borehole is only 2 centimeters in diameter, and we apply 3 combinations of loads on it. The equipment is called a true triaxial testing equipment, which means we can apply 3 different loads on it from the 3 different directions. So we have sigma 1, sigma 2, and sigma 3 acting on every side of the sample. After we apply the loads, we can take CT scans across 18 different cross sections. So those CT scans are taken across different depth points from the core sample. After that, we can run the CT scans through the image analysis code as we have shown before, and you can generate a failure map. So you can know where the borehole has failed and by how much it has failed in every depth point in that sample. Next, we can model the sample in the finite element method. So that's without the image analysis technique and without the machine learning algorithm. So we recreate the geometry and the shape of the sample into the finite element method, and then we apply loads from the experiment in the simulator as well. What we end up with is a conventional prediction of failure. So we are still using the conventional methods to predict failures. And the only way to do that is to rely on conventional failure criteria, something like Moore-Column failure criteria or the Moji failure criteria. And if we do that, we end up with this prediction. Now, again, that is the conventional method to predict failure from finite element modeling. The red zones are the zones that are predicted for failure based on these conventional methods. Now, if you compare the red zones with the actual failure that took place in the sample, you can easily tell that the prediction of failure doesn't really match the failure that took place in the experiment. So that's basically the area of inaccuracy we are trying to improve on. The shape of the red zone, it has to match the shape of failure we saw from the image to get an accurate failure prediction. Now, here are the results of the conventional method and the proposed new method here. Each row here represents a different experiment. The first column is the combination of loads or forces we are applying on the experiment from the lab. So you can see sigma 1, 2, and 3 from the experiment setup, and each experiment has different combination and ratios of those loads. The second column is the CT scan of the failed experiment borehole. The third column is the translation of that failed borehole into the 3D representation or the failure map, as I have shown you from the image analysis. Here you can see the prediction from the conventional method, which is the 3D finite element. And here's the prediction from the finite element infused with machine learning algorithm. Now, if you look at the red zones in the final column, you can see that the prediction of failure, just in terms of shape, just visually, it matches more accurately with the one from the experiment than the one from the conventional method. However, it still does not match 100%, especially for this experiment. So we are predicting the failure to take place here, but the failure actually took place here. However, it still shows some kind of improvement, again, just visually, based on those 2 images. You can see that the final column matches more accurately with the failure that took place in the experiment. Now let me show you the same results, but with a different context. The first 3 columns, those are experiments that were used to train the machine learning algorithm. The final row is an experiment that was not used to train the machine learning algorithm. So the algorithm has not seen this experiment to predict failure. Now, if you look at this column here, precision and F1 score, those are 2 parameters used to qualify the performance of a classification algorithm. So as you go higher towards 1, That's the highest accuracy you can get for classification. And as you go lower, you have a poorer performance for classification. Now, as you can see, the conventional method, it has performed poorly when it comes to classification between failure and non-failure in each space in that 3D sample. If you look at the integrated model between the machine learning algorithm and the finite element model, you can see it has performed a bit better than the conventional method, but still it was not perfectly matching or predicting the failure in those samples, even in the ones that we are using to train the sample itself. Now, if you look at the bottom here, again, that's the only way we can actually judge the performance of a machine learning algorithm is by using a data point it has not seen in the training process yet. If you compare the conventional method with the method used with machine learning algorithm, you can see that the failure prediction accuracy has almost doubled. So we are not perfectly predicting the failure in each data point, but we are improving on the current process. So that's the main advantage here. Now, I would like to show the same results again, but with yet different context. As you can see here, the prediction of failure from the machine learning adjusted finite element model matches almost perfectly with the actual failure that you see in the experiment. So if you look at the red zone, they match with the failure that took place in each one of those experiments. Now, this is only possible if we can train the algorithm with heterogeneous high resolution properties and directional properties of that rock sample. Now, when I say high resolution, it means that we need to know the variation of the strength of that rock sample in each data point, in each location in the 3D coordinate of that sample. Now, getting that kind of data, even in a lab environment, so needing to know what is the strength of the rock in each point in the 3D space is a tricky issue, even in a lab environment. Actually, to get this data, we had to do something called micro indentation, just to see how the strength varies from one location to the other in the sample. However, if you go to the field, that is near impossible. Actually, with the current technology, that is impossible to get this kind of variation of heterogeneous properties along the resolution of the borehole. So it is only possible with lab-based experiment, but it does show the potential of this kind of modeling scheme in predicting rock failure up to high levels of accuracy. And this brings me to the last part of the talk, which is the application of this modeling scheme in a field environment. Now, just like you have seen in the lab experiments, and instead of using a CT scan, we can now use images from the field, which are mainly ultrasonic images and resistivity-based images. So we can read those images and convert them into a structure of the failed borehole. Now we can know what is the failure in my borehole in each well and in each data point, or in each depth point in each well as well. Now that when we are comparing wells data to experimental data, there is one more obstacle. The stresses and forces applied on a sample in the lab is set by the scientists themselves. So we can actually choose what is the stress we apply on the sample. However, in the field, that information is not something that we set, it's something that we need to actually estimate. So the in situ stresses, the forces by the earth crust basically acting on the borehole has to be estimated. So that's one more uncertainty that we will have in the field, which we do not have in the lab experiment. So to be able to do that, we need to gather information from all the usual sources. So we get data from leak-off tests, from mini-fracs, from triaxial lab experiments, from core plugs. We also get data from caliber logs, from wireline, and also from image logs, as I have shown you, to show the failure. Finally, we also get data from drilling records. So any mention of wellbore instability, stack pipe incidents, hole cleaning issues, all those can be used to conclude some kind of wellbore rock failure that can be used to enhance the failure prediction from field data. So the idea is that we can gather all the data from all the offset was available to us, and then fill the data into the modeling scheme. So into the image analysis, finite element modeling, and then finally into the machine learning algorithm. And we end up with that same model we developed for the experiment, but this time for the field. So that's the basic idea. Now, to show you the value of this modeling scheme, I'll show you one example well where it can be applied on. This is a vertical well. It drilled up to a depth of around 13,000 feet, 16-inch in diameter. This is a high-strength sandstone gas reservoir. Now, this well is drilled in a strike-slip regime, which means that the in situ stress in the horizontal direction is higher than the stress in the vertical direction. Now, the well, while drilling, experienced quite a bit of drilling difficulties. We actually faced so many stack pipe incidents, lost circulation events, hole cleaning issues. Eventually, we had to drill 2 side tracks to reach the total depth and the target point of this vertical well. Now, the most important piece of information here is that this well was drilled with a mud weight based on a pre-drain geomechanics model to prevent this kind of failure. So even though the drilling engineers actually did their due diligence to determine the mud weight that can prevent those failures, we still experienced those failures up to the extent where we had to drill 2 side tracks to reach the target point of this well. Now here's the application of the modeling scheme in a real-time environment. Before we drill the well, we have information from offset well logs, and we can build our model based on that information. Now, what we get, again, is a drilling window, a maximum mud weight and a minimum mud weight, and we can select our preferred mud weight between those 2 values. And that's what they did in this case. So that's the actual mud weight they selected in this well based on the pre-drilling model. Now, as we drill ahead, we get more information. This information can be in the form of an image log from LWD tool, logging while drilling. If we get this information, that tells me the wellbore is no longer uniform in shape. It has already experienced some kind of enlargement. I can now rerun the model and reproduce the new results. Again, the same data can be generated not only from an image log, but also from monitoring of the shale shakers. So if you don't have the image log, you can get similar data from shale shakers monitoring. But the end result here, once we reflect the actual shape of the wellbore on this model, we end up with a new definition of the drilling window. So the dashed lines is our new window. And if you compare the solid lines, these 2, with the dashed lines, you can see that the size of the window has shrunk quite a bit, and the selected mud weight lies right at the minimum requirement, which means that the mud weight they selected, the brown curve, lies at the green dashed curve, which is the curve that will incite more wellbore enlargement, which is what explains the stack pipe incidents and all the other issues they face in this well. Now again, if we drill ahead, we can get more new information. This again can be from an image log or just from monitoring of the shale shaker, showing that we have lost circulation. Now, losses mean that we have fractures. If you reflect the fracture on the 3D model structure, you can again reproduce the recommendations for the drilling engineers. Again, once we reflect those fractures and their presence on the wellbore, we can redraw the window, and we can recommend a new mud weight based on that. So that's basically the modeling scheme and how it can be used in a real-time environment to improve the efficiency of the drilling process and eliminate non-productive time. So that's the basic idea. Now, I'll end my talk with 3 more examples from the field of how we can utilize this methodology to improve the efficiency of the drilling process. The idea from those 3 examples is to enforce the application of drilling geomechanics in a more dynamic and responsive manner than what we are doing right now. So the first example is monitoring of the shale shaker. As I mentioned at the beginning, we can monitor the shale shakers to detect any abnormal rock fragments. So if you have an abnormal rock fragment, we can know that this fragment is not produced by the cutting action of the bit. It's actually produced by wellbore collapse. However, detecting those abnormalities visually and manually is not an easy process. So the idea, we can install a camera on the shale shaker, And from that camera, we can just automatically detect those abnormalities using off-the-shelf computer vision algorithms. So, and that's what we did in this case. You can see that's the rig floor right here. And here is the shade shakers. The trailer we see here with the solar panels, it houses the camera. So we have a camera here pointing at the shade shaker. And the image you see here is the video from the camera. So it tells me what is coming on the shade shaker from the analyst, basically. The idea now, we can still, I mean, it's still challenging to detect those abnormalities, even from the video, sitting comfortably at your desk office. But we can employ a basic computer vision algorithm that can detect those abnormalities for us. And that's what we did in the next step. So the idea, we can do something similar to history matching, reservoir modeling, but we can do now caving matching in ring engineering. So from the 3D visualization of the cavings that we saw on the shade shaker, as you can see here, we can match those visualizations to the failure that we can predict from the finite element model, and we can then improve the prediction of the failure just based on that shape and the 3D structure of those abnormalities from the shaker. So that's the basic idea here. It's an inverse problem. You know what is the failure on that borehole, and you can then set up the model to predict that failure just based on the data you have from the shade shaker. Now let's think about those cavings once more. Cavings are basically solids you are introducing into the annulus. Of course, the annulus is filled by drain fluid, mud, which is a non-Newtonian fluid. As you add more solids to drain fluid, it will increase its thickness, its viscosity, its density. So it will basically affect its rheological properties. The idea from this model, if we can predict the volume of those cavings, so all the extra rock fragments and solids you are introducing from wellbore collapse, if you calculate their volume, in case they are unavoidable, you can design the drain fluid rheological properties with that information in mind. Now you can see here a curve of ECD and cavings volume. ECD, of course, is the equivalent circulating density, which is the combination of the hydrostatic pressure of the mud column along with the frictional losses from flowing that mud column upward in the annulus. So as we lower our ECD, we be reducing the support that is needed to prevent wellbore enlargement. If we reduce the ECD and we reduce the support, we get more enlargements. So as you can see here from this 3D visualization, with lower ECDs, the wellbore size becomes bigger. That's the basic idea. Now, the challenge here is that this simple phenomena, it has two countering effects. On one side, you are adding more solids because all those failed rock fragments are going into your drain fluid stream in the annulus. So those extra solids are going to increase the thickness of the fluid. So higher viscosity, higher yield point. As you increase the viscosity and the yield point with drain fluid, you will increase the frictional pressure losses. So you will need more energy to push that fluid upward because it's a thicker fluid now. So you will have that issue on one hand. On the other hand, you are also increasing the flow area because the wellbore size is increasing with the enlargement. This will have a countering effect. As you have a higher flow area, you will have a lower annular flow velocity. And with the lower flow velocity, you will have a lower ECD at the end. So balancing those two countering effects is not an easy issue. But the goal here, if you can actually define the volume of those rock cavings, you can actually define the changes to your drain fluid properties in real time. So what you see here is the plastic viscosity, BV, and the yield point, and the mud weight, which is the density of the drain fluid. So those three properties are the main properties we need to calculate rig hydraulics parameter. So these are the parameters I need to set my bump rate, my standby pressure, and my hole cleaning objectives. So if you know how those properties can change as you are introducing more solids from wellbore collapse, you can define and design a drilling fluid that can overcome NPT, non-protective time, in a more efficient manner. The final example here is geometry. Now, the shape for the well bore can play a big role in defining its failure limits. And the two examples you see here is key seating and side tracking. In this specific case, we had this well that experienced a key seating incident. Key seating occurs when the drill pipe is resting on one side of the borehole, and it is creating a groove or a channel as it drills on that side of the borehole. And as you can see, that's the shape of the drill pipe that drilled this channel at the bottom of the borehole in the horizontal section. The idea is that we can detect the same failure from the image log. So that's an image log from the same well, and you can see there's like one channel of enlargement taking place on one side of the borehole. So once we reflect that change in geometry in the well bore shape, we can recommend a new mud weight to prevent further failure from that well. The other example is side tracking, which is a very interesting problem that we faced in some of our wells. Now, when drilling a vertical well, we usually drill with a certain mud weight and with certain drilling fluid properties. However, once we start drilling a sidetrack from the same well, so once we initiate the sidetrack from the same well, we start experiencing difficulties when it comes to stack pipe incidents, tight spots, and well bore instability that was not experienced in the mother bore. So that was the question from drilling engineers. I'm doing the same formation with the same parameters and almost at the same direction at the initiation point. How am I experiencing different problems in the sidetrack initiation point? Now, the idea is that when you are drilling the mother bore, the vertical portion here, you are drilling into a virgin environment. So the stress environment for the mother bore is undisturbed. Once you drill the mother bore, the stress environment around it is affected and concentrated by the presence of the mother bore. So the only way to counter this is to basically account for the presence of the mother bore on the sidetrack to prevent failure, especially at the initiation interval of that sidetrack. So again, that shows you how geometry in general and just structure can affect the recommendation output and its accuracy. Now, that's the last part of my talk today, which is the results of applying the same modeling scheme to some of our wells. Now, you see here well A, that's the well we applied this modeling scheme on. Wells B, C, D, and E, those are offset wells that are within 2 kilometers away from our target well. So as you can see, 800 meters up to 1600 meters. Now, all these wells, they experienced a lot of well-bore instability issues, stack pipe incidents. We have lost some BHAs in some of those wells, and all of that is due to inaccurate prediction of rock failure. When it comes to this well, once we applied the modeling scheme I've shown you here, we were able to overcome the MBT. So you see here in this column, that's the non-protective time for each well. And in those wells, you can see it's from 600 to 200 hours lost in just combating those challenges from well-bore instability. In this case, we were able to reduce the MBT down to 0. However, we were not able to actually prevent well-bore rock failure. So the images you see here, those are cavings from the shell shaker we collected from the field. And even after completing that well and running wildland logging, we did encounter quite a bit of well-bore instability. However, if you can predict that failure ahead of time, you can give drilling engineers the margin to plan ahead in terms of drilling fluid design, hydraulics, mud pressure, to overcome the MBT that might result from it. So that's the basic idea here. So with this, I'm going to end with this question. How is this different from prevailing practices? Well, first, this relies on elastoblastic finite element modeling, when most solutions in the industry rely on linear elastic analytical solution. Next, most solutions in the model in the market rely on pre-drilling models and a static window definition. So the window is the same limits all along until you finish drilling that well. The idea here, we can actually provide a dynamic window estimation while drilling from this modeling scheme. The next one is that the solutions in the market, they don't consider anything that has to do with the wellbore shape or the wellbore structure. And with this modeling scheme, we can actually rely on image-based or shell shaker-based structural analysis of the wellbore to provide the recommendations. Finally, the output from geomechanics modeling, especially from all the solutions in the market, is usually confined to drink fluid density, only mud weight recommendation. As I've shown you now in the last few slides, the recommendations extent can go beyond mud weight, all the way up to the rheological properties, the hydraulics parameters, and the whole cleaning objectives. So the idea, we can use geomechanics to inform not only mud weight, but also other drilling parameters to improve the drilling efficiency process. With this, I conclude my talk. Everything you've seen here is in the public domain from those references and others, which we can share with you later on. And before I end, can I go next, please? I would like to ask you to take some time to evaluate the talk today. SPE is constantly looking for ways to improve the way those lectures are delivered to its members. And if you evaluate the lecture today from the code on the next slide, you will get a chance to enter your section in a prize draw from SPE International. So with this, I conclude my talk. Thank you for listening, and I'll be happy to take your questions. Thank you.
Okay, definitely we have time for questions. We can come back to this QR code later at the end as well. If you have any questions, please raise your hand and let me know your names.
Okay, thanks for the good talk. My name is Newman. So when we try to take a look at this application, especially like caliper data, sometimes we see this like spiral holes or even like one weak side. Then we think that this could be related to like, if let's say you see spiral hole, probably repeated mortars, right? And then key seat could be like something that the pipe is forced on the one side. So we think that this could be related to mechanical things like mortars, but not geomechanics.
Mm-hmm.
But how do you differentiate that, whether this is a mechanical things that doesn't relate to mud weight or something that related to geomechanics that can be controlled by the mud weight change?
Yeah, the two examples you mentioned, the patterned failure like a spiraled wellbore, that's definitely related to BHA design. Definitely, it's not directly related to geomechanics. So unless there are some bedding pattern, in most cases I've seen it's related to BHA design. The same goes for key seating. It's also related to BHA design. But the idea I'm trying to transmit here is that once you have that spiraled wellbore failure pattern, then you can reproduce the recommendations based on that pattern. So the goal is to prevent exacerbation of that failure using geomechanics principles. Again, you cannot prevent that kind of failure from geomechanics modeling on its own. It's mostly from the tool side, from BHA designs, I would say. Yes.
Any other questions?
Hi, my name's Ian. We've got 40 units for Saudi Aramco. I just want to say thank you for mentioning mud logging and all the other things we can do. I believe you know Ahmed and Farooq very well. We use shale shaker measurements and cameras all the time with Saudi Aramco. And it's such a pleasure to see it being used finally. So thank you very much indeed for your talk tonight. Thank you.
Well, Ian, we are very, very grateful for your mud logging services, really, because one of the most common comments I get when I talk about the shale shakers analysis and detection of cavings is that how can you, for example, how can you correlate whatever you see on the shale shaker to a certain depth buoyant, and my answer is mud logging usually. So
Yeah,
you have,
it is vastly underrated, and thank you so much
Yeah.
for realizing how good it is. Thank you. Thank you.
Thank you, Ian. Thank you.
Hi, thank you for a good talk. Damrong Sak from Valera Energy. You mentioned about you utilize the LWD, some stuff like that.
Yes.
Is that I'm not so sure if like shear, LWD, sonic, something like that. You need to do the post processing after you retrieve the data, and then you do the processing real time and then apply to your model.
So when I refer to LWD, I was referring mostly to density-based image logs.
Density based, but
Yes, yeah.
Is that also you have enough time to do the processing for that kind of thing, or you just do the raw sector image?
Oh, so that's the main reason I was using the term near real time. So in most of those cases, especially with something like finite element, not only, so there's some lag time from both processing the data and also for running the finite element code. So definitely it's something that will cause some lag time if you have that data, of course, but the application is mostly near real time. Yes. Yeah.
Thank you.
Yes. Yeah.
Any more questions from the back? Students?
My colleague.
Oh.
Let's give it to the student first.
No, you go ahead.
Yeah. Thank you, Hussain. It's a great work. I can see a great value with the capability to update the model real time, right? And then you try in one field, that one vertical well, right?
Yes. Yes.
The thing that I could see that you had 4 offset wells, or 4 or 5, which mainly horizontal well, right?
Yes. Yes. Correct.
And then your trial is on vertical well.
Yes, that's correct.
So, don't you think that it would be better to compare with one horizontal to the horizontal well offset? Because normally the geomechanic study, we try to run it for the horizontal well, right? Where this window is narrow sometimes,
Yes. Yes.
mainly for the wellbore stability on the
Yes.
mechanical stress side.
Yes. Yeah. Yeah.
And if you want to have a real good comparison, that
Yes.
could be better to do the field trial with the horizontal and then
Yes.
compare with the horizontal, right? This
Yeah.
is my first point. And the second point, in the offset well, you had one vertical, right?
Yeah.
So for that one vertical, do you have any table to show the difference between the mod weight selection, the one that we did conventional, and the one that we did with the real-time updated model?
Oh, for the offset well.
Yes.
Yes.
So for
Yeah.
the offset well, to see how was the mod weight schedule, and then for this updated, the real-time selection model, what
Yes,
was the mod weight selection, and
Yes.
what's the difference between these two?
Yes, so I'm going to start with the second point. So the vertical well I used to explain the real-time application, the one where they experienced like the side tracks to reach the total depth. That's one of the offset wells we used to compare. Now, I'm not sure if the same offset well from the table, but it is like a vertical well, and you can see the comparison you mentioned in the real-time slide, which is showing the mud weight they selected, and they went with while doing that well and whole section, and the mud weight that was recommended by the model at different time points from the drilling process. But I'm not specifically sure if the same well from the list. I do know they experienced quite a bit of MBT.
Yeah, my point of question regarding the 2 vertical wells, I just want to know that are those drilled more or less in the same pressure regime? Or, for example, the one in the offset well you drill with 12 ppg, and the one in the trial you drill with 9 ppg. So these are 2 different stress regime, right?
Yes.
So
Yeah.
how close were those 2 vertical wells to each other?
In terms of mud weight, you mean?
Yeah.
In terms of mud weight.
Mud weight represent the bubble pressure.
I know that the vertical well was drilled. I don't have the number off the top of my head. I know it was drilled with a much lower mud weight. We use BCF, so I cannot do the conversion in my head quickly. So look, the offset well, especially the vertical ones, were drilled between 80 BCF to 85 BCF, and the one with the model was drilled around like 90 BCF. I think there was a good separation of the recommendations of the mud weights used in the offset well and the well we trialed the methodology on. But I see the point you are trying to make. Definitely there is some value in showing that.
Thanks.
Yeah.
Thank you very much.
Yeah.
That's my
Yeah.
question.
So I'm going to go back to
Very
your
good
first
work.
point. I didn't address your first
Yes,
point
sure.
about comparing vertical to horizontal.
Sure.
That is a great point. I think because I've heard the same comment several times, and it's an extremely valid comment because usually horizontal wells are more challenging, so you expect to face more MBT from those. However, in our case, because we are running in a strike slip regime, so your maximum horizontal stress is the highest stress. It's higher than vertical stress. So we expect failure to take place mostly in the vertical direction. So the severity of failures is usually more in the vertical direction than in the horizontal, just in this field specifically. However, just the accumulation of MBT hours is going to be more just because we drill longer in horizontal interval. So definitely that's a point that we considered. But I only used one of the wells in the example here, but it's something that we addressed later on. But that's a great point.
Thank you.
so much.
Thank you so much.
Thank you.
Okay, we have time for one last question.
I think we would like to hear younger voice.
Yes,
Do you
student.
have any question for the students?
If no question, we're going to ask you to derive the equations. Come on, students. Okay.
Come on, don't be shy. Okay. You look like you have a question.
Hi, my name is Valentin. I am a freshman of Chulalongkorn University Geology Science. So I want to ask you on the graph that you showed, this precision and below is a bracket of F1 score. What is F1 score?
Which one you talking about? Sorry.
You remember slide number?
On the precision, this below is F1 score. So I don't know what is F1 score. So can I ask you what's it for?
Which one? Precision.
This one here.
This the one?
This is the one?
Yes.
Okay, go ahead. So you want the definition of those two parameters?
Yes, yes.
Okay, so those two parameters, again, those are parameters from a machine learning that define the performance of a classification algorithm. So whenever you are classifying data points into one class or the other, so you have two classes, failure and non-failure, you produce something called the confusion matrix. So you have true positive, false positive, true negative, and false negative. Those two parameters, the precision, it shows how accurately you are predicting the failure nodes, so the failure data points, and the F1 score, it shows you how accurately you are predicting the failure and then non-failure nodes in a combined fashion. Now, I can show you the math for both of them later on, if you would like me to do that. But that's the basic idea for those. So it's basically classification accuracy based on the confusion matrix calculation.
Thank you, sis.
Thank you.
Thank you very much. May I give a round of applause to Dr. Hussain?
Okay, so on behalf of SPE Thailand, may we invite Kun Rono, our section president, to give the token of appreciation. Please.
Okay. 1, 2, 3.
I think right now everyone thinking about the equations and models. But don't forget your lucky draw. Write your name in the paper and give to our hotel staff. This is your last chance. In our next meeting, we have Dr. Suplak from Department of Mineral Fuel, DMF, in the topic of the beginning of Thailand journey in CCS development. In October, we have a special event of SPE Thailand E&P Award. September this year. So please check in our SPE Asia Pacific upcoming events for more information. Right now, 15 to 17 May, right now, we have the Future Asia Energy Transition event. Students can join this event for free. Please register. Next one is SPWLA event with Kun Patipat from Scientific Dealing. Next in line will be Associated International Energy Negotiator. Many keynote speakers from Thailand, such as Kun Mundri and Dr. Sean, are the keynote speaker here. And back to Bangkok in August. SPE IADC Asia Pacific Drilling Technology Conference and Exhibition in Bangkok. In October, 6 to 9 October, SPWLA Asia Pacific Regional Conference 2024 at Central Grand Lat Pao. There are many ways to still get in touch with us, like Facebook page, LinkedIn, and I recommend Line Official. You can register it from your line. It will directly link to our website. And it's the time for lucky draw.
Please present. We have 2 prizes, so let's do one at a time.
Yep.
That could be fair.
So today we got the tumbler. It's raining a lot, so if you want some water, you can open the cap and
So
let the rain fill it up for you.
the first winner is Melada from Chevron.
Woo, congratulations, Kap.
There you go.
Thank you very much
Congratulations.
for your speech.
One more tumbler.
The second winner is Frank Timmons.
Congratulations, Kuntai.
So kind to draw my card. Okay, 1, 2, 3.
Thank you, Hussain.
Coming back to our sponsors, if you want your name, company name to be here, feel free to reach out to us. And thank you, Hussain, for sharing knowledge about geomechanics in improving our drilling operation. So If you have time for this night, feel free to be at Rendezvous, the new one, right? The first floor. Thank you.
Okay. So don't just leave yet. We have distinguished measure section evaluation on the screen. So please maybe take your mobile phone and snap it. Then give the feedback to our speaker. So we put a nice score. We're gonna see you again. All right. Okay. Please. Thank you.